In a previous video, we were talking about how electric potential and electric field are very much related. So we already know in an electric fields are created by charges, and they point, and they've been defined to point away from positive charges and towards negative charges. If we were to draw an electric field of a point charge, it would be extending radially outwards from the charge, since I've chosen to draw a positive charge. Electric potential, if you recall, a potential difference, a delta V, is equal to the negative integral of E dotted. We have this written as a ds in the test notes as a generic displacement or direction. I'm going to write this as a dr at the moment, because this equation, with it being a dot product equation, it tells me that we will see a potential difference if we move parallel to an electric field line, which hopefully makes sense. When we talked about a point charge, the electric potential around a point charge depends upon the charge itself and how far from the charge we are interested in. So for example, if I was looking at the same, that's not a very good circle, I apologize. But if I was looking at the same distance around this point charge, please bear with me and pretend that's a nice circle. So assuming this R is the same, I know that if I place a point charge anywhere on a sphere surrounding this Q, this original little Q I drew, then a point charge placed anywhere on that dotted line, and technically three-dimensionally anywhere on the surface that dotted line represents, that point charge would have the same amount of energy. The potential energy of a point charge depends upon its charge and the potential at which it's located. So V, electric potential, is another way to describe the region of space around a charge. So here we're talking a point charge, and so everywhere on this surface would have the same electric potential. Similarly, if we went out to a larger distance r, we talked about this being an equipotential surface, meaning the electric potential has the same value at the same distance from the charge. Okay, so if we happened to be talking about a delta V, meaning moving from one location in space, say a point here to a point here, so a point 1 to a point 2, there would be a potential difference between these 2 points. A delta V of a V final minus V initial. So that's what we're talking about, is a potential difference as we move parallel to the electric field line. Since the electric field of a point charge depends on the charge and how far away from the charge we are calculating the electric field, to move parallel to this electric field, we need to move parallel to R, this R hat direction, that radially outwards. And that's why, coming back over to our equation that relates potential difference to electric field, I want to write ds as a dr instead. Because then since I already know my electric field is in, I'm going to put a subscript of R. It's in the radial direction. That doesn't look like an R. Let me try that again. Since the electric field is in the radial direction, as long as I integrate along a displacement that's also in the radial direction, then I've already accounted for this dot product. I'm moving parallel to the electric field as I integrate. dr means R is our variable. Our limits then are from an initial R value to a final R value. So I want to look at a problem right here that goes along these lines. So I'm just going to rewrite out the delta V that I just wrote above. Again, I'm not writing it as a dot product anymore because I'm already accounting for dr being along the radius. Now this example problem, we have a very long cylindrical conductor with a radius r equals 0.30 meters. It carries a surface charge density, eta, of 38 nanocoulombs per meter squared. We want to find the potential difference between points 1 meter and 3 meters on a perpendicular radius to the axis of the cylinder. I will explain that in just a minute. Keep in mind the electric field on the perpendicular axis is E equals eta times capital R, meaning the radius of the actual conductor, divided by epsilon naught times lowercase r, where that lowercase r is the distance from the axis of the cylinder. Okay, so let's kind of transcribe this and make sense of it. So a very long cylinder, the axis of the cylinder would go down the middle. That is the axis of the cylinder. So coming back to the question, when it talks about the perpendicular radius to the axis, perpendicular to the axis would be this direction. So it's asking about our initial of 1 meter versus our final of 3 meters. So the problem is asking us to find the potential difference, meaning delta V, between this 1 and 3 meters. So between a point right here and a point right here, there's going to be some potential difference, the delta V. And that's what we are looking for. Okay, they've given us the equation that describes the electric field. The strength of the electric field, if we were to draw lines representing the electric field around this very long cylinder, they would be pointing radially outwards. Now I can only draw the two-dimension part in terms of my lack in artistic abilities. I'm not drawing the arrows near the ends of the cylinder because this equation for electric field would have been derived from Gauss's law, and Gauss's law applies in the central region, essentially. Having a very long cylinder implies we're looking in a central region, not near the ends of the cylinder. Okay, so we're looking for a potential difference between here and here. Since there is an electric field, and as we move from 1 meter out to 3 meters, we're moving parallel to the field, then there's a potential difference. And hopefully you recall that electric field lines point from high potential to low. That would mean that the point at 1 meter has a higher potential than the point out here at 3 meters. Our math will show us this as well. So let's go ahead and solve. I'm going to substitute in for the electric field our equation that describes the electric field. And again, it was given in the problem, so I just used that equation. Our limits are going to be from some initial value of r to a final value of r. I'm going to go ahead and pull out my constants. They gave me the surface charge density, 38, so that's a constant. There's no variable part of that. They gave me capital R. Capital R means the radius of this actual conductor that has the surface charge density. Epsilon naught, of course, is a constant. We've been using that already. So we end up with 1 over r. The lowercase r is changing. We have been asked to look at the potential difference between r of 1 meter and 3 meters. And so I cannot pull that out of the integral. Our limits of integration will end up being a lower limit of 1 meter. The upper limit is going to be the upper limit, or the final point we get to, of 3 meters. All right, so I still have eta capital R over epsilon naught. Integral of 1 over r is the natural log of r, which we need to put in. So evaluate between those limits. We put in the upper limit, the natural log of the upper limit minus the natural log of the lower limit. This happens to be the same thing as the natural log of the upper limit over the lower limit. When we have the natural log of one number minus the natural log of another, it happens to be the ratio. Same thing. So I'm just going to set that up, since that just minimizes a little bit of plugging. Let's put our numbers in. So 38 nano, 10 to the negative 9, coulombs per meter squared. Capital R is the radius of the actual conductor. Epsilon naught are 8.85 times 10 to the negative 12. Let's see, our units are coulombs squared over Newton meter squared. Natural log of 3 meters over 1 meter. So the units in here cancel. So let me plug these numbers in. Okay, plugging this in, I'm getting negative 1415 and points other stuff. Revisiting my question though, my distances, my R values that we're integrating between have 2 sig figs. So does the radius of the actual cylinder, as well as the surface charge density. So I should only have 2 sig figs in my answer. I already know potential is measured in volts, but let's run through the units here pretty quickly just to show that we're getting that. So the coulomb in the numerator is canceling with one of them in the denominator. The meter squareds are canceling. So if I bring the Newton up top, I have newtons times meters per coulomb, and newtons times a meter is a joule, so joules per coulomb, which we've already talked about as being a volt. So I am getting volts, which is appropriate. Now this is the potential difference. We're getting a negative answer because, if you remember, delta V means the final value of V minus the initial value of V. Since potential is a scalar, there's no direction associated with it. Getting a negative answer is meaning that V final is less than V initial. As we integrated from 1 meter to 3 meters, we moved from a higher potential value to a lower potential value, which I mentioned this before, just in terms of how we already know electric field lines point from high potential to low potential. But it is also good to just double check that the mathematical solution we're coming up with matches what we know we should be seeing. Okay, I want to talk about one other thing. So, same cylindrical conductor, but I want to change the question slightly and look for the potential difference between R of 0.1 meters and R of 0.2 meters. Now, as a reminder, in the problem we just solved, the conductor itself had a radius of 0.3 meters. So if I draw this cylinder again, or at least a portion of it, here's our axis. This time I'm asking to find the potential difference between 0.1 and, that's a little too far, 0.2. So potential difference between 2 points that reside inside the cylinder. Okay. Now the electric field equation they gave us before, this one, is valid for outside the cylinder. Specifically outside our conductor with a surface charge density. So when our conductor, if you remember Gauss's law, if we were to draw a Gaussian surface, either at either radius, r, 0.1 or 0.2, when we talk about the electric flux through this cylinder, because of the symmetry, we can totally say the flux can be calculated by E times A, but it is also equal to the charge enclosed divided by epsilon naught. But a conductor only has excess charge on the outside surface. So inside the conductor, there's no charge enclosed. In this situation, because of Gauss's law applying, we talked before in the previous section that the electric field inside of a conductor, and it actually is true for any conductor, in what we call electrostatic equilibrium. This means no net flow of charge, net flow or motion of charge. In this case, any conductor in electrostatic equilibrium has an electric field inside, specifically. So inside of 0. Okay. Well, we just used out the equation of delta V is the negative integral of E dot dr, which if we move along the electric field, then we can write this as E times dr. But inside the conductor, E is equal to 0. What this tells me is that inside a conductor that is in electrostatic equilibrium, the potential difference is 0. So coming back to our original picture over here, a point at 0.2 meters from the center versus a point at 0.1 meters from the center has a delta, not the point itself, but there's a difference of 0. What that means is V initial has to equal V final. It doesn't tell us what the value is at either point. It only tells us that the value is the same, which is actually useful, very useful information. It does turn out that the value everywhere inside of a conductor will equal the value of the electric potential at the surface of a conductor. So any conductor in electrostatic equilibrium, regardless of its shape, will have an electric field of 0 physically inside the conductor, and it will have electric potential values that are the same everywhere on the surface of the conductor as well as everywhere inside the conductor. Okay, this is specific to equilibrium though, electrostatic equilibrium. We're going to look at situations in the next chapters where we get a net flow of charge. What we mean by that is current. Amps, how many amps are flowing? Right now in this chapter, we're still going to look at situations involving electrostatic equilibrium. The next thing and last thing we're going to talk about in this chapter are capacitors. We've mentioned a parallel plate capacitor briefly, and we know that it has a uniform electric field. We're going to talk about some other aspects of capacitors as well. We, for now, are only going to talk about the capacitors in equilibrium, meaning no net flow of charge. So these conditions will be met. Now, inside, this E inside means inside the conductor itself, not in the capacitor. So we are not yet going to talk about the time it takes to charge or discharge a capacitor. We'll do that in a couple chapters. So that will come. But for now, we're going to start the conversation at just capacitors that have been charged and are now in equilibrium, so the charge is not changing.